City excitation test part 3. As you know, inductor is a linear element, but if its voltage exceeds a specific limit, the inductor is saturated and entered the nonlinear area. What we mean by saturation of the inductor is the saturation of its core. In fact, when the voltage exceeds the threshold, the core loses its ability to pass more flux, and so it is saturated and the inductor turns nonlinear. But by drawing the saturation curve of a CT, you can see that there is also a nonlinear area in the lower voltages. Up to now, we have said that in higher voltages the inductor becomes excited and turns nonlinear. To explain nonlinear area in a lower voltage, the parallel circuit of a CT is drawn. In this parallel circuit, the turns ratio of the CT, which is a transformer, is 1 to N. Rs indicates the resistance of the CT. In the parallel branch, Rad and Rh stand for Foucault and hysteresis losses of the coil, and L stands for magnetizing inductance of the CT secondary. To perform the excitation test, secondary of the CT is fed by voltage and checked to see what linear element is causing the CT to show a nonlinear behavior even in lower voltages. As mentioned before, the losses of core include Foucault and hysteresis. Therefore, to analyze the nonlinear behavior of the transformer, we need to examine the Foucault and hysteresis losses. Foucault losses are caused by eddy current, which occurs in the core segment because of time-varying flux in the core and voltage induction. Since the flux is directly dependent on the voltage, we can say that the Foucault losses are the result of a pure resistance. The relation of the Foucault losses is achieved through an empirical method and is as you can see. In this relation, V is the flux density, which equals V over F. By substituting this relation, Foucault losses can be rewritten as PF equals V2 over RE. From this relation, it can be deduced that the Foucault losses are caused by a fixed resistance that are not dependent on voltage and cannot be the reason for the nonlinear behavior of the transformer in lower voltages. So it is only possible that the hysteresis losses are the reason for the nonlinear behavior in the CT. Hysteresis losses occur in the core due to the residual magnetism. This means that the passing of the magnetic flux through the metal core in a direction causes the core to be magnetized and turn into a weak magnet. So in the next half cycle, a small amount of energy is lost to remove the magnetic effect of the previous half cycle, and it is being constantly repeated. The empirical relation of hysteresis is pH equals KH FB to the power of X. The value of X depends on the material of the core and can vary from 1.5 to 2.5. Also in this relation, B is the flux density, which equals V over F, and by substituting it, the hysteresis losses can be written as you can see. From the resulted relation, it is obvious that the hysteresis resistance is nonlinear and dependent on the voltage of its two ends. The effect of this resistance in the total equivalent resistance of the CT in the lower voltages is significant, but from a specific voltage upwards, the effect of this resistance decreases and causes the CT current and voltage relation to approach linearity. This causes the relation between voltage and current to be nonlinear in a specific range in the lower voltages.